Okay, this is the video lecture for October 7, in which we're going to be looking at problems from Chapter 9 of Gaskell. Let's begin with problem 9.1. And in this, so I lectured on the thermodynamics of mixing, and if you look at the textbook, the results in the textbook are, and the language in the textbook is parallel to mine. It's a little bit different, but if you skim the book, which you should, because it'll be good for you and me and everyone involved, you'll see how the two are equivalent, and you'll also catch some of the jargon, such as Raoultian solution, which is an ideal solution in which the the activity and the mole fraction are the same. So in this problem, we're saying that we have 1 mole of chromia at 2,500 K, and we're going to dissolve that in a large volume of liquid of this ideal solution, and that solution contains 0.2 mole fraction of chromia plus 0.8 mole fraction of alumina, and they just say it's a large volume, and it's also at 2,500 K. They say, please calculate the enthalpy and entropy caused by the addition. The normal melting temperature of chromia is 2,538 K. And we're also allowed to assume that the entropy of the entropy of melting for alumina and chromia are the same. And kind of the trick here is that in your textbook, if you go back to the appendix where they give you all of the thermodynamic data, they do not give you thermodynamic data for chromia. So that's something they want you to do. So let's do that first here. Let's get some of the thermodynamic data. So we have delta S of melting, melt, Al2O3 is equal to, and we look up the delta H of melting, MEL, melting, of Al2O3 divided by T melt, which is equal to 107,500 joule per mole divided by 2,324 K is equal to 46.3 joule per mole K is equal to delta S melt Cr2O3, and then we're given the melting temperature of chromia, which tells us that delta H melt Cr2O3 is equal to delta S melt Cr2O3 times Tm is equal to 46.3 times 2538 delta H melt Cr2O3 is equal to what do I have here? 117,399 joule per mole. Okay, so we got the latent heat of transformation and the change the entropy that goes with that as well. Well, we said this is a Raoultian solution, which means that finding the enthalpy is equal to 1.17 times 10 to the 5 joule per mole. So that is the same. Basically, we're saying that when the chromia is put into the solution, there is a change due to it melting, but there's no change due to the intermixing, right? Because it's, by definition, doesn't interact. So that gives us the enthalpy, and now the entropy well, there's going to be a contribution to melting, delta S melt, and delta S of mixing. Because remember, when we were doing the ideal solution had the entropy coming purely from configurational. So that is 46.3, and delta S of mixing is minus R natural log of the activity. And in this case, the activity and the mole fraction are the same. So that's going to be XCr 203. So here we get delta S is equal to 46.3 minus 8.314 natural log 0.2. That is equal to minus 13.38. So delta S is equal to 59.7 joule per mole K. Okay. The next problem, let's look at problem 9.2. And in problem 9.2, we're saying if you have 1 mole of gas that bubbles through a large volume of a mixture of iron manganese, in which the composition is given as a 1-to-1 ratio of manganese to iron, and you're given the temperature, and when we do that, the large volume changes mass by 1.5 grams. And the pressure is 1 atm, the gas leaving. Determine the activity coefficient, gamma, of manganese. Okay. So gamma, Mn, zoom out, is equal to activity of Mn divided by x Mn. So in order for us to determine, so we know that's 0.5, for us to determine that we need the activity. The activity is the partial pressure of manganese in the mixture divided by the partial pressure of manganese if it were pure manganese liquid. So these are both liquids. So we have a liquid mixture, and we're saying what is the partial pressure of manganese over that liquid mixture, and this is the partial pressure of manganese over liquid pure manganese, and that's our activity, which then gives us the activity coefficient. And if you go back to your textbook, there's a table in the back that gives us the partial pressures of species that are over top of liquid, a pure compound or pure element, and that gives us the natural log PMN 0 is equal to minus 33440 divided by the temperature plus negative 3.02 times the natural log of the temperature plus 37.68. And in this case, the temperature is 1863 Kelvin. So substituting in here and here, we get the partial pressure of manganese over pure manganese liquid at 1863 is equal to 4.9293 times 10 to the minus 2 atmospheres. Okay, so this is going to go into here. And now we need the partial pressure of manganese over the over our mixture. And by definition, that's the mole of manganese gas over mole total gas. We're told that it's 1 mole of argon gas that's put through, and that has gas has absorbed manganese. So the total mole of manganese that has been absorbed, we're told that this decrease in the amount or in the mass of the liquid mixture is due to the manganese evaporating. So that tells us that the mole of manganese that goes into gas is 1.5 gram divided by 55 point, or it's called just 55 gram per mole. So that. And then the total mole of gas is equal to 1 plus 1.5 gram divided by 55 gram per mole. That is that, which gives us 0.26, try it again, 0.02655 ATM, which now means that the activity of manganese in solution is equal to 0.02655 divided by 0.049293 is equal to 0.5386, which means that the activity coefficient of manganese is equal to over XMN is equal to 0.5386 0.5386 divided by 0.5 is equal to 1.08. And that's how we solve problem 9.2. Now let's solve problem 9.3. Problem 9.3 is got a bunch of parts in it. We'll come to those. So the variation with composition of the excess Gibbs free energy for liquid iron manganese at 1863 K is given here. So that's our data. Does the system exhibit regular solution behavior? Calculate the partial molar excess free energy for iron and manganese, given that the mole fraction of manganese is 0.6. Calculate the total molar Gibbs free energy at for mixing at a mole fraction of 0.4 manganese, and then calculate the partial pressure of manganese and iron exerted by the alloy when the mole fraction of manganese is 0.2. So this whole excess, it's a term that talks about the free energy that is in excess of the rule of mixtures. See the unmixed, and it's the excess in addition to the entropy of mixing. And we're basically talking about the I'll talk about this for a regular, then GXS is equal to omega X FE X MN. Right. This is the term that we saw when we talked about a regular solution. Which means that if this works, then we should be able to say that omega equals GXS over XMN 1 minus XMN, right? So that's X iron, which means that omega 0.1 is equal to 395, that's from our data, divided by 0.1 times 1 minus 0.1, and this we can compare to 0.9, which is equal to, again, 395. Oh. And this is times 0.9, 1 minus 0.9. So it turns out, right, that is 395 over 0.1, 0.9. 395 over 0.9 times 0.1. These two are equal. And they're equal to 4389, 4389. Great. But those are on the two ends. Let's try something in the middle as well. Let's try omega 0.5 is equal to 0.5, 1100 divided by 0.5 times 0.5 is equal to 4400. And these are almost the same. So the answer to part A is yes. The excess free energy seems to obey the expression for the mixing. Okay. The next is we have to look at the partial molar quantities of iron and manganese, or the free energy of iron and manganese. And bar XS of the ith species, that is equal to, let's call this actually the eighth, we're just going to say we have an A-B binary. That's going to be equal to omega times x b squared. And this is just from your text, which means that G bar XS MN, G bar XS FE is equal to omega 0.4 squared omega 0.6 squared. Well, omega we have here, and we have data for 0.6. Well, I guess they're the same, right? Because it's symmetric, because we're dealing with a regular solution. So this is going to be equal to 1054 over 0.4 times 0.6 times 0.4 squared. This is going to be 1054 divided by 0.4 times 0.6 times 0.6 squared is equal to 703 joule per mole, and this is equal to 1581 joule per mole. So I got the solution to that. Yes, it's B. And look at the next part. Whoops. Shuffle my papers over here. Part C. Part C, we are supposed to find the molar Gibbs free energy of mixing. And to do that, we have delta G M is equal to RT X iron, so mole fraction of iron, natural log mole fraction of iron, plus X Mn ln X Mn plus omega, the mole fraction of iron, and the mole fraction of manganese. Right, this is exactly what we did in class. Delta Gm is equal to 8.314 times the temperature, which we're given is 1863, times 0.6 natural log 0.6 plus 0.4 times natural log 0.4 plus 1054 divided by 0.6 times 0.4 times 0.6 times 0.4, so those go cancel, and we get delta G M is equal to -9370 joule per mole. And last but not least, we're going to do D. So D is talking about the calculate the partial pressure of manganese and iron exerted by the alloy when the mole fraction of manganese is 0.2. So this is going to be the activity of some element is equal to the partial pressure divided by, so that's the activity in a solution, it's the partial pressure above the solution, and this is the partial pressure above elemental of that species. So Pi is equal to AI Pi 0. We're solving for the partial pressures, and this we can take from the appendix in the back of your book. So here we have P Fe naught is equal to negative 45,390 divided by T minus 1.27 natural log of T plus 23.93, and the partial pressure of manganese is equal to negative 33440 divided by T minus 3.02 natural log of T plus 37.68. And for both of these, T is equal to 1863. Substituting in there, and there, we get 4.55 times 10 to the minus 5 atmospheres. That's the partial pressure of iron. And the partial pressure of manganese is 4.93 times 10 to the minus 2 atmospheres. So that previous problem where we said that the most of the weight loss was due to the manganese, that's because the manganese has a significantly higher partial pressure, so it's much more apt to migrate or to evaporate. So now we got these, which we have for here. We need the activity, and for the activity, we're going to use the expression that the natural log of the activity of species A is equal to the mole fraction of species B squared omega divided by RT plus the natural log of XA. So this is nominally over here. So if you look in your textbook, you'll find an expression for the natural log of the activity coefficient is equal to this term. And then recognizing the activity coefficient is the activity divided by the mole fraction, that gives us this term. So here we have the natural log, of the activity of the manganese is equal to 0.82, that's the mole fraction of iron, squared times 703 divided by 0.8 times 0.2, that's the omega, just using the that expression from before, and the data set we're given. Then that means divided by RT, 8.314 times the temperature, 1863, plus natural log of 0.2. That gives us the activity of manganese equals 0.2398. The natural log of the activity of iron is equal to 0.2 squared 703 divided by 0.8 times 0.2 divided by 8.314 times 1863 plus the natural log of 0.8. Basically they're exactly the same except these terms switched. And that gives us the activity of manganese is equal to 0.80913, which means now that the partial pressure of iron is equal to this is equal to the activity of iron 0.80913 times the pressure of iron above pure iron at 1863, which is up here 4.55 times 10 to the minus 5. Partial pressure of iron then is equal to 3.68 times 10 to the minus 5 atm. And then the partial pressure of manganese, Pmn, is equal to the activity of manganese, which is 0.2398, times the partial pressure of manganese above pure manganese metal is 4.93 times 10 to the minus 2. So the partial pressure of manganese is equal to 1.18 times 10 to the minus 2 atm. So the partial pressure of manganese is 3 orders of magnitude greater than the partial pressure of iron in this above this mixture. Okay, so let's now work on problem 9.4 from the text. And 9.4 is asking us to calculate the heat required to form a liquid solution at that 1356 K, starting with 1 mole of copper and 1 mole of silver at 298 K. And then the book gives the molar heat of mixing of liquid copper and liquid silver. And my book's old, so it has a little typo, but it should be minus 20,590 times the mole fraction of copper and the mole fraction of silver. Okay. And because we have 1 mole of each, we know that XCU and XAG are both 0.5. Okay, so this problem is asking about the heat required. So that is the change in the enthalpy. And when we talk about this change in enthalpy, the first thing we're going to have to do is we're going to have to start at 298, which we know for both of these elemental compounds is 0, because that's the reference as a solid, but then they have to become liquid, which means that we have to go from 298 up to their melting points, go through a latent heat of melting, so adding the energy for that, and then take the liquid from its melting temperature up to the reaction temperature, or the mixing temperature, which is 1356. Okay, so let's do let's do copper first. In the case of copper, copper's melting temperature is 1356. So that means that for copper, without the mixing, the change in the enthalpy is simply integral from 298 to 1356 1356 times the molar heat capacity of copper, dt, plus delta H melting of copper, which, using the table from the back of your textbook, turns into the integral from 298 to 1356 of 30.29 minus 10.71 times 10 to the minus 3 t minus 3.22 times 10 to the 5 t to the minus 2 dt. So that's the integral. And then the enthalpy of melting is plus 12970 joule per mole. So this is equal to 21833 plus 12970 is equal to 34803 joule per mole, and we have 1 mole. So we have 32,000 kilojoule, or 35,000 kilojoule. Okay, now we'll do silver. And in the case of silver, silver melts at 1,234. So we'll have to do the integral from 298 to 1234 of the heat isobaric constant, or isobaric molar heat capacity of solid silver dt plus delta H melt of copper, or sorry, of silver, plus the integral from 1234 to 1356 of the heat capacity, molar heat capacity of liquid silver dt. So writing this out, we get the integral 298 1 2 3 4, and then the heat capacity is 21.30 plus 8.54 times 10 to the minus 3 times t plus 1.51 times 10 to the 5 t to the minus 2 dt plus the latent heat of melting at the melting temperature, which is 11,090 joule per mole, plus the integral from 1234 to 1356 times the heat capacity of liquid silver, which is just 30.50 dt. And these together give us 26444 plus 11090 plus 3959, which is equal to 41493 joule per mole times 1 mole. So that gives us the enthalpy to raise the temperature of silver solid to 1356 and transform to liquid. Okay? So So the next thing is the excess enthalpy. Excess enthalpy. And that is minus 2590 times 1 minus the mole fraction of silver times the mole fraction of silver, and it's a 1-to-1 ratio, so that is 0.25. 0.5 is equal to minus 5148 joule per mole. But now we have 1 mole of copper and 1 mole of silver, which means we have 2 mole. So that gives us minus 10 to 95 joule, which means that delta H is equal to 34803 plus 41493 minus 10295. Delta H is equal to 6.60 times 10 to the 4 joule. And that is the heat required to form a liquid solution of 1 mole of copper and 1 mole of silver at 1356 K, starting from solid constituents at 298 K. The final problem we're going to solve in this set is problem 9.5, which is asking us to calculate the omega for mixing and calculate the activity of tin when you have a mole fraction of tin that is 0.5 at 500 C, which is 773 K, and we have 473 C, which is 746 K. It's kind of one of those annoyances. You find textbooks that think putting in funky units is cute, but no. Let's do this. So, in this, we're given the activity of lead when the mole fraction of lead is 0.1, and we're told to find the omega, and that's just using ln gamma A is equal to omega for RT B squared, right? And we used this formula earlier as well when we were determining the activity for a regular solution. Which this can then like this, we can now write that the natural log of the activity of A is equal to omega over RT times 1 minus XA squared minus or plus the natural log of XA. So here we have an equation where everything is in terms of the A component, saying we have like an A-B binary, which means that omega is equal to the natural log of A, and it's going to be lead, which we're given, minus the natural log of the mole fraction of lead divided by 1 minus x pb squared times RT, which is ln 0.055 minus ln 0.1 divided by 1 minus 0.1 squared times 8.314 times 746. So this is all the basically in the second sentence of the problem. After we have that, this gives us omega is equal to minus 4.578 joule per mole. Okay, and that in a regular solution is constant, which means that we can now go back to this equation and express the activity of tin, the natural log of tin is equal to omega over RT 1 minus XSN squared plus the natural log of XSN is equal to minus 4.578 divided by 8.314 times 773, because for the second part of the problem goes to a slightly higher temperature, times 1 minus 0.5 squared plus the natural log of 0.5 is equal to minus 0.8712, which means the activity of tin is equal to 0.418. And there you have it. That's how to solve problem 9.5.